Today's video is going to focus on acid-base titrations. In an earlier video series, we learned the idea of titration and how it works physically, but now we're going to focus on applying that method to acid-base chemistry, which is actually very common in labs. When an acid reacts with a strong base, the reaction can always be modeled by HA being the acid, so there's going to be some anion there, and that'll be a spectator if it's a strong acid, reacting with hydroxide ion to produce water, and then the anion will be released. So in this titration, we've got hydroxide ion as part of some base like NaOH maybe, or KOH in the burette, and here we've got the acid in the flask, whatever that acid is. The reaction that we're going to look at in particular here is going to be a strong acid versus strong base titration. And we can divide a titration like this into three distinct phases where you have different types of solutions in the flask. Before any base has been added, what you have in your flask is a strong acid. And like all acids, the pH will be less than 7. In fact, it will be quite a bit less than 7 for a strong acid, unless it's very dilute. In the burette, we have hydroxide ion, so the pH up here would be greater than 7, but we're mostly interested in tracking what's happening with the flask here. The first phase of the titration is before you reach the equivalence point, where all the acid in the flask has been neutralized, but after you've actually added some base. So we can see that the level in the burette has dropped. We've added some base to the flask, but not enough to neutralize all the acid. So we have still in the flask a strong acid, but its concentration is reduced for two reasons. One, we've neutralized some of the acid that was in the flask by reacting with the base that came from the burette. But secondly, we've diluted it because we increased the volume. And remember, molarity depends on two things, number of moles and volume. So the volume got bigger, the number of moles went down, so the concentration of this acid is less. That means the pH is still less than 7, but it's higher than it was at the beginning. The next phase of the titration is right at the equivalence point. So in this model here, I'm assuming that 25 milliliters or so, this volume, whatever this is, that would have reached the equivalence point. Here's what that means. The strong acid down here has been completely neutralized. So if our reaction was HA plus OH minus makes water and A minus, the HA has now all been used up. But we haven't added any additional OH minus yet either. So no acid, no strong base is left in the flask, and basically all you have is water, and you have this anion. But if this is a strong acid, that anion won't have any effect on pH. Well, this is a neutral solution then. It's essentially water with a salt dissolved in it. And so the pH at the equivalence point will be equal to 7. If this wasn't a strong acid, that wouldn't exactly be true for reasons that are too complicated for us to deal with right now. How we know that we've reached the endpoint is by the use often of something called an indicator. There are instruments that can be used. A pH meter can actually measure the pH, and if you know what the pH is at your equivalence point, you could use a tool like that. But it's much cheaper and often works just as well to use something called an indicator. Now what an indicator is a dye. It's actually an acid itself, a weak acid, and it changes color when the pH changes. So if we could model this indicator, this dye, as HIN, because it is an acid, when you add a base to it and completely use it up, it changes, it shifts to IN minus. This will be one color, the HIN, and the IN1 minus will be a different color. So with enough base added, you'll shift from HIN to IN minus, and you'll actually see a color change. Here are examples of some indicators. Phenolphthalein is a very common indicator. Its color in acid is clear, and its color in base is pink. So when you see a shift from clear to pink, you know you've added enough base to neutralize, and a little bit more. Methyl orange is a change from pink to yellow. Bromethymol blue is a change from yellow to blue when you change from acid to base. There are lots of different indicators, and they have different change ranges, so they're useful for different types of titration. Phenolphthalein would be a pretty good choice for a strong acid, strong base titration because it happens to change right around the pH that we'd expect at the equivalence point. Here's a little demonstration of 4 indicators and how they change color in different environments. Here we see 4 beakers. Each one of them contains an ammonia solution. And ammonia is a weak base. So we should see the base color of any indicator that gets put in the beakers. I'm going to add indicators, a different one to each beaker. Into this beaker I'm putting methyl orange, and you can see that the base color is a kind of a yellowish orange color. Into this beaker I'm putting bromethymol blue, and the base color looks to be a sort of a blue color. I have that in the wrong spot on my paper, so I switched it. Into this beaker I'm putting thymol blue. Again, we see a blue color in the basic environment. And into the last beaker I'm going to put an indicator called phenolphthalein, and we can see that in the basic environment it's pink. After swirling, the colors are clear and continuous throughout. Now, to change the environment, I'm going to add an acid, and to this set of beakers I'm going to add 3 molar hydrochloric acid, which should change the environment from basic to acidic. Into the bromethymol blue beaker I'm adding HCl, and we see that the color change goes from blue to a sort of a pale yellow. In the video it may look clear, colorless. Into the methyl orange beaker I add the acid, and the color changes from yellow to a pink or orangish color. Into the phenolphthalein I add the acid, and I change to a colorless solution, and the thymol blue changes from blue to a pink. Now we see the basic colors of all these 4 indicators. After the equivalence point, so the equivalence point was somewhere here on the burette. Now we've added additional hydroxide to the flask. Now remember, all the strong acid, all the HA, had been neutralized. So what we've done here is we've taken a solution that was essentially water and added a bunch of hydroxide ion. So after the equivalence point, what we have is a strong base solution. And the strong base solution has a pH greater than 7, like all bases would. Let's take a particular titration, and we'll generate some values of pH at several different spots during the titration. So here's the setup. We have 1 molar NaOH in the burette. In the flask we have 25 milliliters of a 1 molar HCl solution. And the first question we're being asked here is, what volume of NaOH would be added at the equivalence point? Well, here's what we have to neutralize. We have to neutralize 25.00 milliliters of a solution that has 1.00 moles of HCl per liter, or per 1,000 milliliters. How would this happen? Well, the balanced equation would be NaOH plus HCl makes H2O, or HOH, plus NaCl. So the stoichiometry shows a 1-to-1 relationship between HCl and NaOH. So I'll add that in to my calculation. 1 mole HCl is neutralized by 1 mole of NaOH. So HCl moles are gone, milliliters are gone. What I have is moles of NaOH, and what I really want is volume. But I can change that by using the molarity of the NaOH. I know that there is 1.00 mole of NaOH in every 1,000 milliliters of the NaOH solution. So when I cancel out the moles of NaOH, cancel out the 1,000, cancel out the ones, I find out that the same volume of NaOH is needed as the HCl that I had to start with. And that's because they happen to be the same molarity. So that's the equivalence point. When the level drops to here, to 25 milliliters, I will have reached the equivalence point for this titration. Well, this first question is asking us to calculate the pH in the flask before any NaOH has been added at all. Let's do it. pH is, by definition, the base 10 logarithm of the H plus concentration. HCl dissociates this way. HCl makes 1 H plus and 1 Cl minus. So whatever the concentration of the HCl is, which is 1.00 molar in this case, that's also the concentration of the H plus. So the pH is minus the base 10 logarithm of 1.00. And that ends up being the log of 1, 0. And that's to be expected with a strong acid like this. Next question. Calculate the pH after 15 milliliters of NaOH has been added. So now we've gone down from the 0 mark to 15 milliliters, and that has gone into the flask. Now we know that we'd have to get down to the 25 milliliter point to reach our equivalence point from the previous calculation. So we're not quite at the equivalence point. That means we still have a strong acid in this flask, but it's not as strong. How strong is it? Well, we can use stoichiometry to figure this out, and I'm going to introduce a device called the Rice chart that sort of clarifies the stoichiometry for a situation like this. So I'm going to write down HCl plus NaOH makes H2O and NaCl. This is the R part of this chart, and I stands for initial, and C stands for change, and E is going to stand for end in this particular Rice chart. Alright, so initial means at the beginning. How much HCl did we have at the beginning of this titration? Well, let's calculate that here. We know that we had 25.00 milliliters of our HCl solution, and the HCl solution was 1.00 moles per liter, moles of HCl per liter. So that gives us the number of, but instead of liters, we probably want 1,000 milliliters in here so that we can cancel that unit off. So this gives us 0.02500 moles of HCl that were originally in the flask. So I'm going to put that in my Rice chart for initial, 0.02500 moles. Next I want to find out how much NaOH has now been added to the flask. Well, I know I've added 15 milliliters, and I know that it's 1.00 moles of NaOH per 1,000 milliliters, and so this would work out to 0.01500 moles of NaOH. So I'm going to put that in for my initial NaOH value, 0.01500. And H2O and NaCl, I just really don't care what's happening with them at this point. I'm mostly interested in how much HCl is left. Well, if I look at these, there's one-to-one stoichiometry, and so that means the fewest number of moles is going to be the limiting reactant here. So what's the change? I'm going to lose all of the NaOH, all 0.01500 moles. And since it's one-to-one stoichiometry, I'm also going to lose 0.01500 moles of HCl. So when this is done reacting, I would have in my flask no NaOH, and I would have the difference between 0.02500 and 0.01500, which is 0.01000 moles. And since HCl is monoprotic, that means I have 0.01000 moles of HCl, or H+, in, well, what's my volume now? I put in 25 milliliters into my flask originally. That's 0.02500 in liters. Plus, then I added the base solution, which is another 0.01500 liters. So now I have moles per liter concentration of H+. When I work out the arithmetic, it comes out to 0.2500 molar. So the pH at this point is the opposite of the base 10 logarithm of 0.2500. And that works out to, I'm going to round all of these pHs to 2 decimal places, which is a pretty reliable practice most of the time, 0.60. So my pH is higher than it was before, but it's still pretty low, indicating that it's still a strong acid solution. Now it's asking me to calculate the pH after 20 milliliters of NaOH has been added. So I'm going to set up another Rice chart. So my reaction line is going to be, again, HCl plus NaOH makes water plus NaCl, and I don't really care about that part of it. What's the initial? Well, we already have figured out that we had 0.02500 moles of HCl in the flask before we added anything. Now we've gone from 0 down to 20 milliliters, and 20 milliliters is 0.02000 in liters. So if I multiply 0.02000 liters times 1 mole of NaOH per liter, it tells me that I've got 0.02000 moles of NaOH that will have gone into my flask. So I'll put that in here, 0.02000. What's my change? Again, NaOH is the limiting reactant because I have less of it here. So I'm going to lose 0.02000 moles of both of these. So at the end, I don't have any NaOH in my flask, and I have 0.00500 moles of HCl, which means 0.00500 moles of H plus are in my flask. And now the volume is going to be the original 25 milliliters, or 0.02500 liters, plus the 20 milliliters that I've added from the burette, 0.02000 liters. My molarity is now 0.11 molar. So that means my pH is the negative of the base 10 logarithm of 0.11 molar, and that ends up being 0.95. So the pH is still pretty low. It's not even reached 1 yet, but it's higher than it was in the last calculation. Now I'm supposed to calculate the pH after 24.90 milliliters of NaOH has been added. We're really close to the end point now. The equivalence point was supposed to be at 25 milliliters. We're not quite there yet. We've gotten just down here to 24.90 milliliters, which is 0.02490 liters of NaOH added. So let's set up another rice chart here. The reaction again is HCl plus NaOH, and it's one-to-one stoichiometry, and it makes products that we've already decided we don't care about. My initial values, I have 0.02500 moles of HCl in the flask at the beginning of the titration. Now I have added, you can do the calculation, but it's going to be 0.02490 moles. Every time I add a liter, I'm adding a mole. So if I've added 0.02490 liters of NaOH, I have added 0.02490 moles of NaOH. So what's the change? Well, we're really close to NaOH not being the limiting reactant, but it still is. And so we're going to lose 0.02490 moles of NaOH from the initial NaOH, and we're also going to lose 0.02490 moles of HCl. So that at the end, we're going to have no NaOH, and we are going to have 0.00010 moles of HCl left. So what's our concentration? Concentration of H plus is going to be 0.00010 moles of H plus in our total volume, which is now 0.02500 liters plus 0.02490 liters. So it's very close to 50 milliliters right now, and our molarity when we work this all out comes out to 0.0020 moles per liter. So our pH is now negative base 10 logarithm of 0.0020, and that pH is 2.70. So the pH is now climbing. It's higher than 2, but it's still definitely in the under 7 range, and we're within 1/10 of a milliliter, which is just a couple of drops, of being at our equivalence point. Next question has us at 25 milliliters, and that is the equivalence point. What's the pH here? We don't have to do a calculation. We could, but we already know that the pH is going to be 7 at the equivalence point because this is a strong acid, strong base titration. Next question is asking us to calculate the pH after 25.10 milliliters of NaOH has been added. So now we've gone to the end point and a little bit beyond by adding 0.02510 liters of our NaOH solution. If you look at the flask, you notice that it's changed to pink now, and that's because my HCl that was originally in the flask has now all been used up, and I have now added an additional amount of my base, NaOH. So what I have in the flask now is a strong base solution. I'm going to set up a rice chart again. So reaction line, we already know what this is HCl plus NaOH. Initial moles. Well, I had 0.02500 moles of HCl there, and now I've added 0.02510 liters of NaOH, which is 0.02510 moles of NaOH. So now, after the equivalence point, HCl is the limiting reactant. And so I will have lost all of that number of moles from both quantities. And that leaves me at the end with no HCl and 0.00010 moles of NaOH, or moles of OH minus, because NaOH provides one OH minus per formula unit. So my concentration of OH minus in the flask now is 0.00010 moles divided by the total volume, which is going to be 0.02500 liters, the original volume from the HCl, plus 0.02510 liters that have been added from the burette total at this point. The concentration of OH minus is now 0.0020. So that means the pOH is equal to minus the base 10 logarithm of 0.0020, and that ends up being 2.70. Sort of a mirror image of the pH when we were 1/10 of a milliliter on the other side of the equivalence point. But pH is what we're interested in, and pH is 14.00 minus pOH, so that leaves us with a pH of 11.30. Now here's an astonishing thing. If you think about it, in the space of 2/10 of a milliliter, which is about 4 drops, our pH went from 2.70 all the way up to 11.30. And in the whole previous 24.90 milliliters, it had only moved from 0 to 2.7. So there's a dramatic change in pH that happens right around the equivalence point. And that's what makes this indicator work so well. That rapid color change happens within just a few drops, and it allows us to very precisely tag where the endpoint happened. The last iteration here says to calculate the pH after 30 milliliters of NaOH has been added. Well, we can set up another Rice chart again. Reaction line is HCl plus NaOH, making products we don't care about. Initial values. The HCl, of course, is 0.02500 moles. The NaOH that we've added now, well, 30 milliliters is where we're at this point, and that's 0.03000 liters. At 1 mole per liter, that means we have added 0.03000 moles of NaOH. HCl after the endpoint is always the limiting reactant, so we're going to lose 0.02500 moles of each. And that will leave us in the end with no HCl, and at this point, 0.00500 moles of OH minus. So the concentration of OH minus now is those 0.00500 moles of OH minus divided by the total volume, which is now 25 milliliters, or 0.02500 liters, plus 30 milliliters, or 0.03000 liters. The concentration you end up with when you do this calculation is 0.0909 molar. So the pOH is the minus base 10 logarithm of that 0.0909, and that ends up being 1.04. So pH is 14.00 minus that 1.04, and that leaves us with a pH of 12.96. So we've added a considerable amount of NaOH, but the pH has risen not incredibly much. So in these phases of titration, you can see that if you plotted the volume of OH minus added versus pH, it's a slow change at first, then a dramatic change right around the equivalence point, and then it goes back to being a slow change. I'm going to put all these numbers in a graphing calculator and display that for you so that you can see that the very values that we have calculated are going to show the same story. So here you can see in list 1 and list 2 I've put the values that we calculated for pH in list 2, and in list 1 I have the volumes that we had for all of our calculations. And I'm going to make a stat plot, so I'll go second function, stat plot key, and I'm going to turn this plot on. I'm going to make this a scatter diagram my X list is going to be my volume, and that's L1, and my Y list is going to be the pH, which is L2. And then I'm going to quickly graph this by doing a zoom stat. And here's what I find. I'm going to go back and change my plot just a little bit to connect the dots. Instead of a scatter diagram, I'm going to make a connected scatter. And then look at the graph again. And that's pretty much what I traced out. If we had had more points, it'd be smoother. But you can see, again, that dramatic shift from low to high pH right at the equivalence point. It's almost a vertical line. And that makes our indicator very effective at detecting the endpoint. This is a smoother picture with a lot more data points of this kind of a titration. And you can see the three stages are distinct here. Stage 1 is before you reach the equivalence point, you have a strong acid solution, so the pHs are all below 7, and there's a change, but there's not a dramatic change in pH. It's sort of a straight line that slopes up. Then right around the equivalence point, you see this huge change in pH. For this particular titration that they have on this graph, it went from 5 to 10 in the course of just maybe a few drops. And then that's stage 2, the equivalence point. And then stage 3 is when the concentration of OH minus is much bigger than the concentration of hydronium, and you have a strong base solution, and then the pHs are all above 7, and it increases but gradually. Well, in the next video, we're going to use the idea of a titration and the idea that this rapid change exists right around the equivalence point to see how we can determine the concentration of an unknown acid or an unknown base by relying on that rapid color change for an indicator.